Hello students, welcome to Gate Electronics Guruji classes. In this video, we are going to start the topic transformations of continuous time signals. So before going to learn the different transformations operations, let us first try to understand what does transformation means. Transformation is nothing but an operation by which one signal is converted into another signal. Suppose we have a signal x of t, and after transformation operation we obtain the signal y of t. The signal x of t is termed as the parent signal or original signal, and the signal yt, which is usually different from that the signal xt, is termed as the transformed signal or converted signal. Transformation operations can be categorized into three types. One is called the scaling operation, one is termed as shifting operation, and one is termed as reversal operation. We will explain it later that reversal operation is not a new operation, rather it's a special case of scaling operation. Each of the three operations, that is scaling, shifting and reversal, can further be subdivided into two categories each. Scaling can be of two types. The scaling operation can be performed either on time, termed as time scaling. It can be applied on amplitude, termed as amplitude scaling. Similarly, shifting operation can be applied either on time axis, termed as time shifting, or on amplitude axis, termed as amplitude shifting. Similarly, reversal operation is of two types, either time reversal or amplitude reversal. In this video, we are going to learn what does time scaling means, and we will take two examples to have a better understanding of the concept of time scaling operation. So let us come to time scaling. How do we define the time scaling operation? Expansion or compression of one signal in the time domain is termed as the time scaling operation. In the time scaling operation, the amplitude of the original signal remains unchanged. Only the signal gets either compressed in the time domain or gets expanded in the time domain. Let us try to understand what does actually happen in a time scaling operation. Suppose we have the original signal denoted by xt. After time scaling operation, suppose we obtain the signal denoted by yt. Then yt is defined as yt is equal to x of alpha t. If we compare the original signal xt and the signal we obtain after time scaling operation, that is yt, we observe that yt is different from that of xt, because in xt, in the argument of the signal we have t, but in the argument of yt, that is in the argument of x of alpha t, we have a constant alpha multiplied with the time t. This constant alpha is also termed as time scaling factor. Alpha can have any real value, but alpha cannot be 0 or 1. Now let us try to understand why alpha cannot be 0 or 1. If alpha is equal to 0, if I put 0 in place of alpha, we will have x of 0 into t. We are putting 0 in place of alpha. So then yt becomes x of 0 into t, which is nothing but x of 0. X of 0 is not a signal, rather it's a constant value. Hence alpha cannot be 0. Now let us understand why alpha cannot be 1. If you put 1 in place of alpha, we will have yt is equal to x of 1 into t, that is x of t. So if you compare the original signal xt and the signal will obtain after time scaling for scaling factor 1, which will also be equal to x of t, we see that no change is occurring on the signal. So when the scaling factor has the value 1, there is no real significance. Depending on the value of alpha, the time scaling operation can be categorized into two types. In case 1, we have if modulus of alpha is greater than 1. That is, if alpha lies in the interval minus infinity to minus 1 or 1 to infinity, we will see later that the original signal gets compressed in the time domain. So this is the example of time compression operation. And when modulus of alpha is lesser than 1, that is alpha belongs to the interval minus 1 to 1, we will see later, we will explain it by example, that the original signal gets expanded in the time domain. So this is the case of time expansion operation. First we will take an illustrative example of time compression operation and then we will go to time expansion operation. So let us have an example of time compression operation case 1. So case 1 is the example of time compression operation. Suppose we have a signal x of t whose waveform is as shown in the figure. We see that x of t is equal to 0 for t greater than 2. X of t is constant at the value 1 when t varies from minus 2 to plus 2 and xt is equal to 0 when t is lesser than that of minus 2. Suppose we have to convert the signal x of t to obtain a new signal yt where yt is equal to x of 2t. So if you compare the original signal xt and the signal we obtain after transformation, that is yt, we observe that t has been multiplied by 2 in the converted signal. So clearly this is an example of time scaling operation with a scaling factor of 2. So the scaling factor alpha in this case is equal to 2 and as modulus of alpha, which is also 2, is greater than 1. So this is an example of time compression operation. Now we have to find how does the waveform of the signal looks like after the transformation operation. Let us try to understand. The rule is, as I have said it before, in the scaling operation the amplitude of the signal remains constant. Only the signal gets compressed or expanded in the time domain. So we will teach you a shortcut method to understand how to get the waveform of the final signal. This shortcut operation can be instrumental for you when there will be a very high time constant as in GATE exam, or you cannot use more than 2 minutes for one question. So let us see how I am drawing the waveform of the signal yt, which is x of 2t. While drawing the signal x of 2t, keep in mind we are actually asking the variation of x of 2t with respect to time t. So the x-axis will correspond to the t variable or the time variable. The rule is, first observe what is the scaling factor. Here the scaling factor is 2. Then you have to divide every time instant in the original signal or the parent signal by the scaling factor. If I observe the original signal, I see that xt is constant at 1 when t is varying from minus 2 to 2 and outside this the value is remaining 0. So divide minus 2 by the scaling factor. Here the scaling factor is 2. So if I divide minus 2 by 2, we will have minus 2 by 2 is equal to minus 1. Similarly, if I divide plus 2 by 2, we will have plus 2 by 2 is equal to plus 1. So the idea is, Here the in the original signal xt was 1 in the interval t varying from -2 to 2. So in x of 2t the value will be 1 in the interval -2 by 2 to +2 by 2. Corresponding to this point, that is -2, we will have a point here which is -2 by 2 equal to -1. Corresponding to this point t equal to +2 in the original signal, we will have the point +2 by 2 in the signal x of 2t, and inside the -2 to 2 in the original signal the value was constant and 1. So in the converted signal also the value will remain constant at 1 in the interval -1 to +1. So that's how you have to draw. But obviously if you use this method in your semester examination, though the answer might be correct, but you are not going to score any marks. So we also need to please the orthodox professors of our college. So we will teach what is the formal method of getting to x of 2t from x of t. Let's try to understand. I am writing this signal, this is the description of this signal in this new page. We had x of t equal to 0 for t greater than 2, x of t equal to 1 when t is varying in the interval -2 to 2, and x of t was 0 when t was lesser than -2. And your professor asks you to find x of 2t from x of t. So let's see how we can do it. The idea is, I am writing this again. You have x of t equal to 0 for t greater than 2. You have x of t is equal to 1 for t greater than -2 and lesser than 2, and it is 0 for t lesser than -2. You have to find out x of 2t. I have said that in time scaling operation, the amplitude remains constant. Only what does change? Only it's the time t that actually gets changed. That is, the signal gets compressed or expanded in the time domain. The idea is x of 2t is equal to 0 for, you had t in the original signal, you will replace t by twice of t because we are trying to draw waveform of x of 2t. So x of 2t will be equal to 0 for all 2t greater than 2. X of 2t will be equal to 1 for all, in place of t we will write here 2t. 2t is greater than -2 and lesser than 2. And x of 2t will be equal to 0 for all 2t lesser than -2. Now just simplify this. You are having x of 2t is equal to 0 for all t greater than 1. X of t is equal to 1 for all. You have twice t varying from -2 to 2. So if you divide 2 everywhere, you will get that t varies from -1 to 1. If 2t is lesser than -2, that simply means t is lesser than -1. You get it by dividing both the sides of this inequality sign, that is this less than sign, by 2. So you have t lesser than -1. So here you haven't even drawn the waveform of xt, but you have got how does x2t varies in different time intervals. And now you can draw the waveform of x2t from this description. You have x of 2t is equal to 0 for t greater than 1. You have x of 2t equal to 0 for t lesser than -1, and inside this interval the value is constant at equal to 1. Sometimes what will happen is that the signal's value will be given in different time intervals like this, and the signal won't be as simplified as in this case. You might not even be able to draw the waveform of the signal, but you will have 4 options, and in the 4 options will be given in this format. That is, you will be given the value of the signal in different time intervals and you will have to choose the correct option. In those kinds of gate problems, you have to do the problem in this way. And also in your semester examination, what you will have to do is that you will, if you are given the description of the signal in this way, that is the value is given in different time intervals, and you are asked to find out x of 2t, then you have to follow this procedure to get to x of 2 t. So I hope that it is clear up to this part. Now let us come to case 2, that is the case of time expansion. Suppose we have the original signal x of t, which waveform looks like this. Xt is equal to 1 when t is varying from -2 to +2. When t is greater than 2, you have x of t is equal to 0. When t is also lesser than -2, you have xt equal to 0. And suppose we have to convert this into a new signal yt, where yt is equal to x of t by 2. Now, if you compare x of t with x of t by 2, you will see that while going from xt to x of t by 2, the t variable, the time variable has been scaled by a factor half. Don't think that here the scaling factor is 2. Scaling factor is the constant that we multiply with t to get to the new signal. Here we have multiply half with t to get to the new signal. So the scaling factor here is half. So the scaling factor alpha here is half, and clearly modulus of alpha, that is half, is lesser than 1. So this is clearly a case of time expansion. So if this is asked in a gate problem, we will do it in this way as I have mentioned it before. First draw the time axis t, draw the amplitude axis, which is x of t by 2. Then what you have to do is that corresponding to every time instant in the parent signal, you have to divide it by the scaling factor. Here the scaling factor is half. So if I divide -2 by half, you will have -4. Dividing -2 by half, you will have -4. Dividing +2 by half, you will have 4. In this case, x of t was constant at 1 when t was varying from -2 to 2, and outside it was 0. So in the new signal, x of t by 2, the value will remain 1 when t will varying from -4 to 4. The value will remain constant at equal to 1. You have to simply divide the different time instants in the parent signal by the scaling factor to get the new signal. So that's how the waveform of the signal looks like. And if you compare this signal with this signal, you observe that the signal has actually been expanded in the time domain. Clear? And similarly, in the last case, if you compare the parent signal with the obtained signal, you see that the new signal was actually compressed in the time domain. So that was the case of time compression. Now let us come back to this. Now, if the question is such that you cannot draw the waveform of the parent signal, and the 4 options in the gate examination are in this format for the final signal. That is, it is given x of t by 2 equal to this, for t less than this, it is equal to this, for t varying from this to this, or equal to this, from t greater than this. Then without being able to draw the waveform of the original signal or the parent signal, we need to know how can we get to the new signal. So let's see how I am doing this, just as in the previous case. In place of t, I will write t by 2 everywhere. I have said that in time scaling operation, the amplitude remains constant. It's only time axis that either gets compressed or gets expanded. The signal gets either compressed or expanded in the time domain. So x of t by 2 equal to 0. Wherever we have t, we will replace it by t by 2. So I am replacing t by 2. So we'll have t by 2 lesser than -2. Similarly, it equal to 1 for all t by 2 greater than -2. In place of t, I am writing t by 2 or lesser than 2, and it is equal to 0 for all t by 2 greater than 2. In place of t, I am writing t by 2. So if I simplify this, we will have that x of t by 2 is equal to 0 for all t lesser than -4. If you multiply both the sides of this inequality by 2, you will have t lesser than -4. From this inequality, you will have x of t equal to 1 for all t lesser than 4 and greater than -4, and x of t equal to 0 for all t greater than 4. So even without being able to draw the waveform of the parent signal, you now know how to get to the final signal. So I hope that it's clear up to this part, and in the next video we'll learn about amplitude scaling. If you have any doubt regarding the time scaling operation, please let me know in the comment section. And if you have any suggestion regarding my channel, please be free to let me know about that. And if you think that you are liking my video, then please subscribe to my channel, because it's your likes, your subscriptions to my channel, and your comments that actually motivate me to make more and more videos for you. Thank you.